Annihilation study of bone-implanted PMMA. This research is carried out in cooperation with researchers from Japan, Egypt, Slovak Republic, and Russian Federation. In the content, they will be focused on ion implantation of polymers, bone-implanted polymetallic methacrylate, positron annihilation spectroscopy, and positron annihilation lifetime spectroscopy, and Doppler broadening of annihilation line, slow positron beam spectroscopy, and the stopping and range of ions in matter simulation, temperature-dependent positron annihilation lifetime spectroscopy, melt simulation of free volume distribution, and changes of molecular weight in polymer, conclusions, and what next. Ion implantation of polymers is effective technological method to turn dielectric polymer to conducting semiconductors. For example, Vladimir Popov showed as model the reason for this effective technology is appearance of carbonization processes upon ion implantation. As a model, it is shown that carbonization process depends on implantation fluence, and as here see the formation of precarbon structures, nucleation and growth of the carbon-enriched clusters, aggregation of the clusters resulting in the formation of network conjugated bonds, transition to amorphous carbon or graphite-like material. So in this research, we study bone-ion implanted polymetallic methacrylate. We produce this sample, as far as we know, for the first time, and here we see our investigated samples according to a dose of ion implantation. So we use for the first time also the positron annihilation spectroscopy techniques to investigate carbonization processes in ion implanted polymeric materials. One of these methods is positron annihilation lifetime spectroscopy. The thermalized positrons can be trapped and annihilated in vacancy time defects, giving information around, about environment around defects and free volume. The more important for polymers is the existence of positronium, which has a lifetime of more than 1.5 nanosecond. The positronium is the bond state of the positron and electron having atomic radius comparable to the hydrogen atom. Positronium exists in two spin states. One is called as parapositronium, in which positron and electron spins are antiparallel, and another one, orthopositronium, when the positron and electron spins are parallel. So parapositronium to orthopositronium are related in the ratio of 1 to 3. So in vacuum, orthopositronium has very big lifetime, 142 nanometers, but due to peak-off annihilation process in material, the lifetime of orthopositronium is significantly reduced to few nanoseconds. And when we studied materials with positron annihilation lifetime spectroscopy, and we see the lifetime, the few nanoseconds, we can make conclusion that we have formation of orthopositronium in this material. So the typical positron annihilation lifetime spectra presented here, we have peak-off annihilation process of orthopositronium leading to the tau lifetime higher than 0.5 nanosecond. So another technique is Doppler broadening of annihilation line. And this technique is we consider in terms of Doppler S and W parameters when the positron annihilate with valence electrons. We have the contribution to S parameter, the shape of the peak. When the positrons annihilate with electrons with co-electrons, we have contribution to W parameter in the wing of the peaks. And sometimes S and W parameter are so-called as valence and annihilation parameter, respectively. Here, as typical, we see the Doppler broadening spectra of annihilation line 511 keV. So when S parameter versus W parameter show us the type of defect structure. According when slope is the same, we have the same type of defect structure, and when the slope is different, we have different type of defect structure. So in this research work, we use unique technique from positron annihilation spectroscopy called as slow positron beam spectroscopy. The measurements were carried out at the National Institute of Advanced Industrial Science and Technology in Japan. Here on this slide we have the S parameter and W parameter as a function on positron energy for the investigated PMMA. We see the two different curves for S and W parameters. When ion dose is small, we have the S parameter increase and V parameter decrease. When ion dose is high, we have the S parameter decrease and V parameter increase. The S parameter increase, it means that free volume or size or concentration of voids increase, and instead of the same is V parameter decrease. So we consider here the two processes. The first process, formation of free radicals at low ion doses, and carbonization at high ion doses. Also, we compare our results with theoretical stream simulation, and we found that in the damaged region, when mean penetration depth of positrons is about 200 nanometer, correlated well with the mean penetration range calculated from stream simulation 253 nanometer. We present the S parameter as a function of ion dose at incident energy of 2.15 and 3.18 keV in the damaged region of polymer. And we see that for low ion dose, we have the S parameter is higher, but significantly decreased with the implantation dose increase. So also the same for 3.18 keV. And this is the evidence that we have carbonization process with increasing of ion dose. In order to obtain also the S parameter versus W parameter, the slope is something different from the damaged region in comparison with oxygenated kapton. So we also consider that as our suggestion that oxygen is removed from the damaged region of PMMA. In order to find additional evidence for carbonization, we've conducted for the first time the positron annihilation lifetime measurements at the incident positron energy of 2.15 keV. And we see when we have for pre-Stein's unimplanted sample, we have, and the sample implanted with lower ion doses, we have the formation of autopositronium. But when we have the high ion doses, we doesn't see the formation of autopositronium. It should be noted that from literature we know that autopositronium does not occur for carbon, for instance for RAN structures. And this is for the first time direct experimental evidence that no observable autopositronium at high ion doses is accordance with the carbonization process in such ion implanted polymers at high ion doses. Another very interesting information can be obtained from temperature-dependent positron annihilation lifetime spectroscopy. We carried out the research work in Institute of Physics of Slovakia. Here we see the autopositronium lifetime as a function of temperature and autopositronium intensity as a function of temperature. We see that three-shoe temperature 170 and 250 K for autopositronium lifetime and autopositronium intensity. Our results at room temperature for PMMA is good agreed with the literature data of Wang et al. And we see the same values of autopositronium lifetime and intensity. Also, our results is in accordance with temperature dependent of positron annihilation lifetime for PMA with different molecular weight, reported by the authors Pujari et al. They also found that for poor PMA, two critical temperatures near the 150 and 250 K. The authors explained the results according to molecular motion in polymer, and the type of molecular motions presented here, and the authors explained the results according to gamma and beta transitions, which occurs at the temperatures below the glass transition temperature, Tg. Also, we can explain our results, the threshold temperatures, 170 and 250 K, connected with threshold gamma and beta transition below Tg. According to literature, the Tg for PMA is more than 355 K. So, but we have between gamma and beta transition, we have for implanted sample, we have like hysteresis curve, and the intensity is not is practically linear function in comparison with the unimplanted polymer, but the values are not so significant different in comparison with the unimplanted sample. So this is a situation at low ion doses, but at high ion doses we have the significant decrease intensity of autopositonium, and the dependence is also linear. So we also may conclude that this process is accordance with the carbonization process in the upon ion implantation of investigated PMA. So, next results we obtained using simulation, melt simulation of free volume distribution, and also we see that firstly, the autopositonium lifetime is found to be good agreement with experimental data, and the intensity, relative intensity, show nonlinear distribution, probably maybe due to nonlinear decreasing of autopositonium intensity in experimental data. But when we have implanted polymer, we have linear distribution, distribution of relative intensity, and also good agreement of autopositonium lifetime. So it may be also in accordance with the linear dependence of autopositonium intensity for both implanted PMA. So also here we have that the free volume distribution for two cycles, heating and cooling, is practically the same. So it's also as evidence for reproducibility of simulation performed. Another very interesting aspect for PMA is the investigation of heat at microorganisms, the PMA, with different molecular weight. And they found that when molecular weight of PMA is very high, we have the broader autopositonium or free volume distribution. And when we have molecular weight is decreased, we have narrower distribution of free volume autopositonium lifetime. So according to this literature data, we analyzed our results for unimplanted and S-implanted samples. And we see at lower ion doses, we have the free volume distribution is narrow in comparison with the unimplanted sample. This process is accordance with the formation of free radicals when we have distortion of bonds. But for S-implanted samples at high ion doses, we have the free volume distribution or autopositonium lifetime distribution is broader. This accordance with the increase of molecular weight in ion-implanted PMA. So, in conclusion, we obtained the results of slow positron beam spectroscopy along with stream simulation as clear confirmation the concept of occurrence of two processes upon ion implantation, formation of free radicals at lower ion doses and carbonization at high ion doses. The temperature-dependent pulse measurements have supported these findings by slow positrons. In particular, the following conclusions we found. The results of depth distribution of implanted layer obtained by slow positrons are agreed with string simulation. Two different processes are seen on the Doppler S and W parameters as a function of positron energy in the range of 0,3 keV, independent on the ion implantation dose. Namely, SE increases when WE decreases at lower ion doses, while SE decreases and WE increases at high ion doses. Also, S parameter at incident positron energy of 2.15 and 3.18 keV decreases sharply when ion dose is larger than 10^16 ions per centimeter square. Slow positron lifetime measurements at incident energy 2.18 keV reveal that the orthopositronium yield only for the pre-Stein sample and the implanted samples at lower ion doses, and probabilities of orthopositronium formation exemplified by the intensity towards some reduction with increasing ion dose, while no any observable orthopositronium yield for the implanted samples at high ion doses. And molecular weight in implanted polymer decreases at lower ion doses, but increases at high ion doses, in consistence with the formation of free radicals and carbonization processes. And what next? We plan to study next xenon implanted PMA, helium implanted PMA, and silver implanted PMA at different ion doses, in order to find how the change of type of implanted ions will affect on the carbonization and free radical formation process. And also we would like to change the matrix. Instead of PMA, we would like to study flexible organic inorganic hybrid rare silicate rare ZIL polymer matrix, and also investigate rare ZIL upon silver ion implantation at different ion doses, and then to have more issue on the subject investigator. Thank you very much for the attention.
As minimum 3 questions. The first one relates to why do you apply for PMA for this resist, very interesting anyway, boron? The first question. The second one, I saw from this positron spectroscopy from Iris Tsukuba that you also compared the results with Kapton. Why with Kapton? Why?
Okay. First question, according to bone implanted PMA, we know in literature information bone implanted different polymers, polyimide and others, and so on, and the effect of bone implantation on the increase in conductivity is published in literature. But no any information, as far as we know, for bone implanted PMA. And we tried this sample for the first. And PMA matrix is very also important because we have from literature as well another carbon implanted PMA, nitrogen implanted PMA, and also the results show the very good results in respect to conductivity increase in the upon ion implantation. So the PMA is very important matrix, and boron we do it for the first time for PMA.
Okay,
and another equation from slow positrons. We compare with Kapton because we have source of positron is covered, is two sides by Kapton. And slow positron penetrate Kapton. And we would like to know information how Kapton, because we have a distribution of defects from surface to the bulk. And we would like to know directly what we have from positron from source, so Kapton and through polymer. And we compare. And thus we make this our suggestion that different slope with Kapton means that Kapton is oxygenated, and different slope, our suggestion, oxygen can be removed from the damaged region.
Over the last 30 years or so, there has been some interest in anomalous dynamics of glasses, both theoretical and experimental. You know all these two-level systems of vibrations, soft potential. But this is basically processes that occur below 20K or so. My question is, have people with positron spectroscopy probed this temperature region? And if not, is it technically possible, and what do you think will it yield something?
there are not so much for glassy material. You talk the glasses, no polymers.
Including polymer glass.
Including polymers. Okay, there are a lot of results for polymers with positron annihilation, temperature-dependent positron annihilation spectroscopy. But a lot of polymers have TG lower than room temperature, and the authors considered the process before TG and after TG. The uniqueness of PMMA, the TG is after room temperature. And when we're down to low temperature, we consider the gamma-beta processes that occurs below TG. It's very important. First, yes.
Okay. Thank you again.
Thank you very much.